All right. Hello, and thanks for joining us. My name is Hoda Azadi with the Federal Highway Administration, and I manage the NDE research program. Thank you for joining another FHWA NDE webinar, and thank you for showing a great interest and for supporting this NDE webinar series. So we started this monthly webinar series a year ago. I see that people are still trying to get in the room, so let me admit them all. So we started this webinar series a year ago with the goal of learning more about how various states are utilizing NDE technologies, their current practices and current applications and case studies, their challenges, added value, their policies, future application with regards to NDE. So this webinar series has provided a platform to the state DOTs to exchange knowledge on NDE technologies in highway infrastructure, also to inform researchers, technology providers, industry representatives about states' current practices and policies, and also their challenges and future directions with regards to the use of NDE for condition assessment of highway infrastructure. So all the webinars are being recorded, and the link to the recording will be provided later in the flyer. Professional engineers who attend the entire webinar as an individual will be awarded 1 PDH. So to be eligible for the credit, the individuals must remain signed in for the entire webinar, including the Q&A session following the presentation. There is a survey after the presentation, and you will be asked to submit your email address and respond to some questions. So please make sure to stay on for the entire webinar. Today's presentation will be given by Mr. Mike Todson, a special project engineer from Iowa DOT. He will be sharing Iowa's experience with the use of NDE and case studies for bridges and bridge inspection. You can type in your question in the chat box, and Mike will answer your questions after the presentation. So I appreciate if you can mute yourself. I try to mute everyone, but if you are not muted, please mute your microphone, and Mike, please unmute yourself. And with that, I pass it to Mike.
There we go. Oh, welcome everyone. I'm Mike Todson with Iowa DOT. I'll try and answer as many questions as I can here at the end, but my email address is there on the screen. If you would like to ask me any questions later on, I'd be happy to take them. I'll be talking about some of our experience related to bridge inspection with using NDE. I guess first start off, why have we been using it? And there's some evaluation that visual inspection simply cannot do. Looking for subsurface flaws or other deterioration that's not at the surface, as well as verifying any surface anomalies, and then to provide more consistent results than you may get from a visual inspection, and take some of the inspector interpretation and variability out of it, as well as there is a potential to increase data collection speed, which makes life a little bit better for everyone. So when did we first get into using NDE in bridge inspection? There's kind of two initial cases. One, I'll get into both of these more later, but first was using equipment called Delamtech, and we're using that for deck soundings. And then using ultrasonic testing for evaluating potential cracks in steel structures. Currently, we use it for deck inspection, which led into some use in substructure as well. Obviously, structural steel is very common, and we're getting more into the instrumentation and health monitoring side of things. We've done some work with some underwater evaluations. I don't know if everyone considers this NDE, but it is provide us with some valuable information. And we're starting to get into the drone activity a little bit. All right, let's start off the deck evaluations. What we're looking for is really a project level assessment so we can use information in the development of plans for repair work. And looking at our typical multi-beam or girder bridges, steel girders or pre-stressed beams make up the majority of our inventory with a concrete deck. And we commonly use a concrete overlay using a low slump dense concrete that other people may have heard of as the Iowa mix. We've been using it for quite some time, and we have now a lot of bridges in our inventory that are ready for the replacement of that overlay, and we'd like to place a second overlay instead of replacing the deck where possible to keep it more economical. But we need to understand the condition of the deck underneath that overlay to really understand what we have to work with. If in an ideal world, we would be scanning a lane width at 45 miles an hour to limit our impacts on traffic. That's really a goal we're not there yet, but it's always something to aim for. And if we could get that, we could move more towards program level assessments where we could collect that on a larger volume of our inventory. And here's some detail on the types of overlays we use. Um, we mill off a 1/4 inch of the original deck and put back 1 3/4 inches of our dense concrete. And at the same time, we'll remove any deteriorated areas in the original deck as partial or full depth repairs. And we'll refill the repair areas monolithically with the overlay placement. Now, when we go to placing a second overlay, the determination of those deteriorated areas in the original deck gets to be the challenge. And just to give you an idea, just a typical spot on the bridge deck that's been milled and the partial depth repair has been cleaned out, ready for placement of the overlay. We place the overlay, we put a slurry coat as a bonding agent, and then place the dense concrete mix on top of there. And one thing to provide some extra life in our overlays, after we start to get some debonding between the overlay and the original deck, or perhaps some deterioration at the reinforcing level and we get some hollow areas, we will inject epoxy to reestablish the bond and add additional life to the overlay. However, this can complicate our evaluation of the deck as it adds another layer of material that you have to take into consideration when performing evaluations. I think we're all familiar with the traditional methods for hand sounding a deck. Obviously, the visual identification, and then by hammer sounding or chain drag. This is fairly time consuming and operator dependent, and especially when relying on the hearing abilities of our inspectors, and when you get around heavy traffic, this gets considerably more complicated. Some of the limitations with the hand sounding or traditional methods. Uh, the delamination of the original overlay from the original deck cannot be differentiated from deterioration in the original deck. Hollow is hollow. It's hard to verify the depth by hand sounding. And really, we're looking to see what condition the deck is in. And then as the deterioration is deeper into the concrete, it can become very difficult to identify it with hand sounding. And of course, the lane closures required not only interrupt traffic, but they also prevent more safety risks to the public traffic and to our staff that are working in the traffic control or in the roadway. And just an example how this can be a problem for us. This is a bridge this is a current project we have. And it's scheduled for a second overlay. When the original overlay was removed, they found a significant area of deteriorated concrete on the bridge deck. This requires a lot of hand labor to clean up and prepare as a repair area, and that can affect the contractor by the requirements for allocating their resources to this project. The schedule is affected as there is a lot more time involved with all the hand labor, and there are budgetary effects to us as the contractor expense of doing this repair is on our burden. And so if we had a method that we could better determine the condition of this deck in the development of this project, we probably would have considered other alternatives and may have looked more at a deck replacement than placing a second overlay. That may have been a more cost-effective solution in the end, had we known ahead of time. But so the testing methods we've been using, earlier I mentioned the DelamTech. This was a system developed down in Texas in the 1970s. That's when we purchased our first machine. At one time we had 7 of them. It's an automated deck sounding machine. It had a little hammer and a silicone-filled wheel with a microphone attached to it, and it could detect the hollow concrete similar to hand sounding. But it did remove the operator variability, and through several rounds of improvements to the equipment, we had an automated data collection system. Unfortunately, the manufacturer of this equipment went out of business a number of years back. At the time, we purchased their entire inventory of spare parts. We have consumed that inventory and no longer have a functional piece of equipment. So we've been trying to find another method to evaluate bridge decks and provide us the additional information we're looking for. We got some assistance with this. We started off with Rutgers University, followed up by some additional work with Jenny. We got involved in the pooled fund with University of Missouri, and then the Sharp 2 program most recently. And we're looking for a practical solution, one that we can deploy readily, and that we can get good correlation with the field conditions. So looking at that project level assessment, we want to know where the areas of deteriorated concrete are on the deck, not just a general assessment of this deck may have some deterioration. With Rutgers, we tried a number of different technologies. Starting off We used acoustic or seismic um systems using impact echo and ultrasonic surface waves. So the impact echo did provide some interesting results and led to some follow-up work, as I'll describe later. Then going on to ground penetrating radar, both ground coupled and air coupled, along with eddy current testing and half cell potential and electric resistivity. One thing I should note here is that in Iowa, we use a large volume of de-icing salts in the winter, which leads to heavy chloride concentrations in our bridge decks. And for these, like the electrical resistivity, our chloride concentration really affects the results you can get there. And then one issue we ran into with the half cell potential, now that we've been using epoxy coated reinforcing in our bridge decks for a number of years, the application of half cell potential has become significantly more difficult, as you need to have contact with the reinforcing steel and getting continuity among the reinforcing mat when it's epoxy coated is extremely difficult, if not impossible. Following that, we worked with Jenny on a few ideas. We got into infrared thermography for the first time for deck evaluations. Some more work on ground penetrating radar. The GPR, it sounds very good for the data collection rate and the availability application, I should say, to use it on a more widespread inventory, or more of our inventory go to more of a programmatic evaluation. So we keep on trying to make that one work. Again, some more work with impact echo, and then half cell potential again. So I mentioned we worked with Dr. Washer down at University of Missouri on their pooled fund with infrared thermography. And that was using these handheld cameras. The basic principle here is that when you have delaminated concrete, it will heat and cool during the thermal cycles of the day at a different rate than the surrounding solid concrete. And the sensors in these cameras nowadays are sensitive enough that they can pick up on that very small difference in temperature. And these cameras are really impressive what they can do. And then also we did a little work with Dr. Washer on ultra time domain infrared, which I'll get to here in a second. But using the infrared cameras on our bridge decks we put quite a bit of effort into making this work, because the application of it we really liked. However, there were a couple things we ran into. One, on our bridge decks in the infrared spectrum, we kind of get this glare that you can see in the photo on the right. And we have worked with changing the direction that we're viewing as related to the sun, the direction that we are shooting going from at the deck. And for whatever reason on our decks, we've had difficulty overcoming this glare issue. And then the other thing we ran into is that through our evaluations, we found out that we could reliably find delaminations up to about 2 inches deep under field conditions. Under research conditions, I know 3 inches is considered a reasonable limit for IR, but for field evaluations, we found that once you got past 3 inches of depth, we would also often get false negative results, and so we've really considered about 2 inches to be a practical limit for our inspection work. With that said, we went down underneath the bridges, and it worked quite well on the bottom of decks. Of course, there we only have about an inch of cover, and are reinforcing it. It worked extremely well there. But then we noticed that it worked quite well on the substructure as well. This happens to be a particular pier that was adjacent to our roadway, and our local maintenance staff was concerned that some of the concrete might be loose enough that it could fall into the roadway. And we're going to go out and hand sound this pier. And I took out the camera with me and was able to collect some images from the ground, and got very clear results on the locations of the delaminated concrete, and showed these to our field staff, and they were very satisfied with the results. They felt it was better than they could have achieved by hand sounding. Doing the hand sounding would have taken a considerable amount of time, would have required a lane closure and bringing out a lift. This took, with the IR camera, took a few minutes with no lane closures, so it was no traffic control, and so it was very cost effective that way. One thing I should note, I've gotten a few questions about. These images are using the rainbow colors and high color versions, and I've found that for people that are unfamiliar with infrared images, that the high color versions are much easier for them to understand. Myself personally, when I'm using it, I now prefer the grayscale images, and I think most people, after they've used it a while, prefer the grayscale over the high color. But for people like these, were to be used by people who hadn't seen many IR images before, and the high color version is just much easier to understand. Apparently, seems to be much easier for them to understand. The ultra time domain infrared. This is kind of an interesting system. Instead of looking for variations in temperature at a particular time, this has a camera set up for an extended period of time. I believe we had this one in place for 12 hours, and it collects images at regular intervals over that time, and then through some data reduction, we get a plot of the rate of change of the temperature. And so the image you see on the left is the areas that are heating and cooling faster than the rest of the bridge deck. And this takes away the variability you get from the time of the day, that you may or may not be hitting it at the right time of the day. And it provided, the center image is, you can see some kind of pink outlines, and you can probably see them a little bit better on the right image where the two are combined. And the outlines are what we did with hand sounding versus the IR image, and I think we had a very good correlation here between the two. All right, moving on then to the Sharp 2 work. We got back in the Impact Echo and did some more work with GPR. Impact Echo, based on our previous work, we think this has a lot of potential for us. And at the time, Olson Instruments had developed their bridge deck scanner. We bought the first one they sold, and it has a rolling transducer array, which really differentiates it from a lot of other Impact Echo systems. It has integrated data collection. You can adjust the scan width, and the important thing here is that it records the full sound wave for later post-processing. We did some initial tests on bridges without overlays, and we had very good correlation with other test methods as well as the repair areas found during construction work. And so the system works quite well. The data collection is straightforward. We can train our maintenance people fairly easy to do the data collection. However, the post-processing does take some more understanding, and I think for our sake, we'll be keeping that as a small group in our office that will do the post-processing. It does require lane closures and some layout work. One thing, the deck needs to be clean of debris, so there's a little work there. And as far as the time is concerned, it takes about the same amount of time to scan a deck using the impact ecosystem as it would hand sounding. However, after talking to some of our staff that I've had do both, they all would prefer using the impact ecosystem over hand sounding. Here's what the system looks like. See on the left, it has 2 sensor wheels. Each of them has 6 transducers in a radial array, and they're 2 are out of phase with each other, so that the 2 wheels do not interfere with each other. The spacing between the wheels can be adjusted, and then that feeds a processing board, which feeds the data then to the data collecting software on the laptop. If you look on the right, you can see there's a small solenoid that acts as a hammer to create the sound wave. And then in the center of the white wheel, there is a small silver dot. That dot is the actual contact surface for the transducer. And one of the drawbacks is that dot has to be in contact with the concrete surface long enough for the sound wave to be recorded, which really puts a limitation on the speed at which you can collect data. And so that's really the controlling factor in the data collection rate. And we end up moving this cart at a few feet per second is about all the faster you can go and still collect good data, which it's almost a chore to remember to go slow enough. Here's it in action. You know, I'm the one back there with the broom doing the tough work. But remember that small transducer that has to be in contact with the concrete surface. So sand, gravel, and other debris need to be cleared out of the way to get good results. And even the paint stripes will affect the results. So when we make passes near the paint stripes, we have to make adjustments to make sure that we are not including those in our data. Of course, there's some learning curve with this. This is one of my original attempts at identifying delamination or deterioration in a bridge deck beneath an overlay. The red and purple spots are the areas that I was estimating, and the black boxes are the areas that were repaired. And this kind of going through this bridge kind of highlighted some of the challenges. The difference between the depth of these repair areas and the bond between the original overlay and the deck were very small depth differences. And in addition, the depth of the overlay and the depth of the reinforcing both varied along the length of the bridge. And so it's a challenge to get good, to narrow down your results to just the deterioration in the original deck and not include debonding of the overlay. But we're working on it. Then the other thing we tried, 3D radar makes a stepped frequency ultra wideband GPR array. Again, GPR just has so many advantages as far as data collection rates that it's hard not to try and make it work. And their system, depending on the system you purchase, can scan 6 to 8 feet wide at a pass at 5 miles an hour. It has a multi-channel antenna with the variable frequency range. It's vehicle mounted, similar to most air coupled GPR, so makes for traffic friendly rapid data collection. Here is an image of it, and in this there are 21. You can kind of think of it as 21 separate antennas in this one piece here, instead of the normal 2 or 3 air coupled antennas you would see with a traditional GPR system. However, we ran into switching to the better GPR or more elaborate GPR system didn't solve all of our problems, and added to some of the question you always get. The images here, the top image is the results based on the 3D radar. The bottom image is the results from a traditional air coupled antenna, and the two are different, and I was hoping there would be some more correlation between these, and quite honest, I'm not sure what to make of this. I haven't quite figured it out. Then we compared it on a couple bridges to repair areas, and again, we just didn't have the correlation to the repair areas that we were looking for. And with the GPR, with what we're finding out is with the volume of salt that we've used and the level of chloride contamination we have in our decks, we get a fair amount of signal degradation as a result of the chlorides. And that signal degradation from the chlorides is easily confused with the degradation you may get from concrete deterioration or rebar corrosion. And so it's really difficult to differentiate what is simply chloride contamination and what is actual deterioration. All right, so more recently, we have been working with a company called Advanced Bridge Inspections. They have an automated sounding system which provides a high correlation to sounding or to hand sounding. It provides for fairly rapid data collection, and it's allowed us to go and do some project or program level data collection as well as project level work. I kind of think of this as the modern day replacement to our old Delamtech machines. There's this system, this is one of their earlier ones. They've made some updates since this photo was taken, but here it's a system spreads out to 12 feet wide. At each foot there, you can see they have a small solenoid driven hammer and a microphone to pick up the sound. The hammers alternate back and forth as they slowly drive across the bridge with this behind them. And essentially it's a acoustic sounding similar to hand sounding, just with an automated side to it. And comparing to hand sounding, you can see the top image is the results of the ABI systems sounding, and the bottom is hand sounding by one of our crews that was done shortly before the ABI system. And to my take, this has a very strong correlation. I'm very satisfied with the correlation in these results. And the benefit is the ABI system can collect this data much quicker and easier than we can. And so we've started using this quite a bit. Of course, it cannot answer our questions about the question of condition of bridge decks under an overlay, but for bridges without an overlay, it's been working quite well for us. Most recently, then, we've also worked with Infratech, evaluating some of their new equipment. And they have two systems: a high-speed system using air-coupled GPR, automated chain drag, IR, visual cameras, laser profiling, and then a low-speed system with GPR, impact echo, ultrasonic surface wave, and electric resistivity. Here's an image of their high-speed system. It has the air-coupled horns in the front, top-mounted cameras, chain drag system underneath the back bumper, and their high-definition cameras are up, or their line cameras are up in the little black boxes on the back. And then they have their low-speed system. This is a bit of a transformer. Kind of interesting to see it on the roadway. It has the ground-coupled GPR, impact echo, electrical resistivity, all mounted in these pods, which are attached to the arms, which unfold from it. And this moves along. This moves a couple feet at a time, and then the arms set the sensors down and collect data, lift them up. The truck moves ahead a couple feet and slowly works its way across the bridge. One thing we found, there's always something you're not expecting. And one of the things with this was they integrated a line scan camera on their system, as opposed to the traditional cameras that I've seen on a lot of other systems. And these line scan cameras have provided some of the best images from a technical aspect that I've seen for evaluating bridge decks. They get the same images day and night, regardless of the sun or shade or clouds, and it's a very high resolution image that makes it work well with crack analysis algorithms, and is so there's always something you can find when looking at new equipment. And another area kind of related to the bridge decks we're getting into is on the curb at the base of barrier rails or curbs, where at the cold joint, where we get some corrosion of the reinforcing attaching the barrier rail to the deck. And you would expect that, now if you can see in these images, there is about a 1-inch gap in the reinforcing between the bridge deck and what is now the bottom of that bar that's supposed to project into the bridge deck. Interesting thing about this is we have not had a good correlation between the condition of the concrete on the surface and the condition of the reinforcing. You would think if we get 100% in section loss in the reinforcing that it would cause some deterioration on the concrete. But we have areas that with complete section loss like this where the concrete will look fairly sound, and we'll have areas where the concrete looks significantly deteriorated, but the reinforcing is still largely intact. So a few years ago, we worked with the Center for Non-Destructive Evaluation at Iowa State to come up with ideas on how to look at this. Again, looked at GPR. Due to the geometry of the location, we had trouble making that work consistently. They put together a system, magnetic flux leakage system that seemed to work. However, it was a one-off kind of laboratory assembled system, and it's a long ways from being ready for widespread deployment in the field. And we looked at radiographic testing, and the radiographic testing works excellent in the lab. However, deploying it in the field was problematic, as you need a significantly larger uh, radioactive source than you would, say, with evaluating a weld in a steel plate due to the thickness of the concrete. And between the regulatory issues and safety concerns, the field application really wasn't practical. So if anyone has come up with a good way to evaluate the uh, reinforcing in that bottom of the barrier rail there, we would be interested in hearing what you have. And so I guess what's next? We're continuing to work with vendors and um, practitioners to improve the results we're getting and try new methods. I'm not sure that the dog here is going to help us, but we're at times really willing to try just about anything. Moving on to other parts of inspection work, structural steel evaluations. Initially, we had UT inspection by our materials fabrication inspection staff. They had CWIs and the equipment, but scheduling time for them to return to a bridge, often with traffic control and a snooper, was just not a cost-effective way to do things. Uh, we then moved into using mag particle inspection, and this is really our main inspection method for evaluating cracks in steel. Important part of that, as you can see on the image there, there's been some grinding of the surface. We all of our teams have angle grinders with flap sanders, and removing the paint and cleaning up the surface can help out a lot in getting accurate results and getting rid of false positive results. And our current practice, mag particle is still our primary method. We use both traditional and phased array UT. Here, like we use the phased array UT is really, I like it a lot. Looking at pins and like this pin and hanger connection in the picture, the equipment is more expensive. It requires more training and is more complicated to set up. But at least in my opinion, the analysis and evaluation of the results as you're scanning are much clearer with the phased array testing than with traditional UT, and for that I think it's worth the additional costs. But phased array does have its limitations. For example, looking at anchor bolts on ancillary structures, we still use phased array because of the limitations in the signal strength produced by the phased array. And we have a number of aluminum sign structures in the state, and we use penetrant testing on those when we need to. I just don't like it other places as much because I don't like getting covered in dye. We've then moved into some of our instrumentation and load rating, or health monitoring, I should say. Initial work was in load rating and fatigue life evaluation. We've done some wind and vibration monitoring, and we're moving more into health monitoring. The load rating original work was to look at bridges with marginal capacity and see if we can refine the distribution factors to improve the load ratings as much as possible. And then we've moved on to evaluating some unique loadings, such as when bridges are used as haul roads by contractors, or for we have a lot of we're farm equipment around the state, and they produce unique loads on bridges too. So understanding the distribution factors applicable to those loads. Um, then we've had one unique kind of feature that we did a lot in the 50s, where we use these tapered cover plate terminations. And we have a policy that if we are replacing a deck on a bridge with cover plates, we have to retrofit the end of the cover plates to avoid fatigue issues. And this tapered detail can be very problematic to cost effectively retrofit. So we've done some fatigue life evaluations on these bridges where we've shown that the stresses are underneath the CAFLs, constant amplitude fatigue life stresses, and so we were able to, through testing, uh, show that the retrofitting was not necessary. Wind and vibration monitoring. This was kind of an interesting one. This is a bridge we have over a reservoir, and under the right wind conditions, we can get some movement in the bridge deck, and through analysis and monitoring, we've found that we can get up to 2 inches of movement. However, that is enough that it causes considerable concern for anyone on the bridge. And we've had people abandon their vehicles and run off the bridge because they thought it was going to collapse. And they felt that the movement was about 2 feet based on their perception while they were on the bridge. So we now have a system where we can monitor the wind speed and the vibrations on the bridge, and we have trigger events set up to notify our maintenance staff, and they will close the bridge when necessary just to avoid the concerns with the public being on the bridge while it's moving. And then we did some initial health monitoring, small scale installations, and really we just were checking the viability of getting the remote monitoring working and sustainable. And we've done a couple full-scale installations. Our initial one was in 2011 on Arch Bridge, where we had a number of sensors located throughout the bridge. And then we've moved on to, we have a pair of arch bridges which are building over the Mississippi River. And as part of the construction, we're installing a health monitoring system there where we'll have over 500 sensors located throughout the arch spans and in the approach spans. And we're working on the question now we're working with is how much data to collect and how to compress it and how to store it, because at their full capacity, these sensors can produce just really a ridiculous volume of data. And so saving all the possible data is just not practical. However, we want to have data that's both giving us information now as to how the bridge is acting, as well and changing a long time, as well as having adequate records so that 20 years from now we can go back and look at what we've done and have valuable reference data. And so figuring out a frequency to collect data, how often to collect it, and such as and how to store that is an interesting question for us. Some other work, the underwater work. We have over 27 bridges and waterways in Iowa. We have no divers, and it's not uncommon to have flood events. And when we do, our water visibility anyway is near zero. So diving has limited effectiveness. And so we're looking for ways to evaluate during the flood damage. There's a few systems on the market. Kongsberg is the one we went with, or Teledyne has one, and Coda Octopus as well. And really, the main thing leading us to the Kongsberg system was cost. It's considerably cheaper than the others. But it allowed us images on the right. You can see pile vents, and you can get a pretty good idea of the condition there. Image on the left, we're able to see this is a small creek, it's a small single span bridge over a little creek that had a large flash flood event. It undermined the south abutment to the point that we lost the fill material behind the abutment, and which we knew, but the question was on the north abutment if we still had fill material, and with the sonar system, we were able to see that we had undermining of the abutment, but we had not lost the fill behind the abutment. And here's another case where it was helpful for us. This was a pair of bridges over an abandoned railroad right-of-way, and during a flood event, our roadway became a levee, and this old right-of-way became a river. We had heavy scouring underneath the bridges, and you can see on the upper right, there's 3 sets of pilings where you can't really see the pile caps on top of them that were heavily scoured out. The south pier on the right bridge has exposed footings, but the pile have not been exposed. And on the left bridge, the south pier has some pile exposure, but nothing to the extent of the other bridge. And so it was able to give us a clear indication what was going on there without that otherwise would have been very difficult to achieve. And then I guess UAS is kind of something we're just getting started on this. We're not nearly as far as some of the other states like Minnesota, but we're definitely interested. Then recommendations I would have for other states is when you're trying something new, make sure you find a champion to work on it, someone who will take interest in it and put some effort into it. It can be challenging, and you need to find someone who's willing to meet those challenges. And then figure out what you need to, what really are you looking for in your information? Not just are you looking for concrete deterioration, but are you looking for steel corrosion? Or what exactly do you need to know to make sure you ask the right questions? Then learn your environment, like ours, the salt affecting the GPR, and what materials you use in your construction that can affect the appropriate tests and the test results. And verifying results. Don't just, because something has worked in another location does not mean it will work for you. That's, I think we found that out to be the case. Then some lessons we've learned. You need to have a basic understanding of technology to make it work. Even if you are hiring outside consultants, know how like I said, know how your practices will affect the results, and work with the vendors. Make sure they have the experience and qualifications that you need, and make sure they understand what your expectations are and what you're looking for in the results. And then people have asked where we find our funding. If you have the state funding available, that's always the easiest. Then going through state research dollars or SPR funds, and then going into the grants such as Sharp 2, Everyday Counts, and such. I kind of rushed it at the end there, but I wanted to leave at least a couple of minutes for questions. And I guess I can go back to the infrared. Where I do think the surface of our bridge decks may have something to do with the problems we're getting with the infrared working correctly. I haven't been able to. We do get kind of a polished surface on the bridge decks, and that may have something to do with the problems we're seeing. We're still working on that. The line scan camera, it's a camera that takes a picture of instead of a very thin width, and then they have that keyed in to collect a specific wavelength of light, and then they have a laser that illuminates the deck at that particular wavelength, so it's only collecting the light or only collecting the image illuminated that by the laser at that particular wavelength for just a very narrow strip. Um, let's see. Decks with a waterproof membrane. We do not have any waterproof membranes in our database or in our inventory. Sorry. So I don't know what would work best with a waterproof membrane. I'm just sorry, can't help you much more there. Um, let's see. Deck condition on a project level, or we collect it right now on project level, but then with the ABI system, we've been collecting data on corridors and working towards more of a program level evaluation where we can make more network level decisions with it. The rabbit. What happened with the rabbit? As I understand, the Infratext system that I showed is the modern iteration of the rabbit. That's what's become of the rabbit. I'm not sure where the rabbit itself is currently at, but that's how we got into the Infratext system. Let's see, the angle of the IR camera will reflect glare. Have you tried looking straight down? Yes, yeah, we did. We tried just about every angle we could perceive, and we just could not overcome that. It's really kind of baffling why we can't. And could you show the IR image that had the, let's see, IR image that had the location superimposed? I believe that was this one. Was that? And, have you tried any methods for finding delamination of concrete covered with asphalt overlays? No, we have not. We do not use asphalt overlays except in very rare circumstances, and that's normally a bridge that's scheduled to be replaced in short order. So we haven't looked at using evaluating bridges decks under asphalt overlays. I guess. I think. How am I doing, Hoda?
It's great. You did a great job, Mike, on the time management, answering the questions. So, and the great presentation, very informative, very interesting to hear about Iowa's experience, how Iowa started with NDE application, challenges, lessons learned. So I really appreciate the presentation. Uh, any other questions you can write in the chat pod. I know that it's 2, but we can stay on for 1 minute. And also I posted the link to the poll and the survey. So please take a moment to take the survey and submit your email address to receive the certificate for the 1 PDH. Okay, one more question for you, Mike.
All right. Let's see. Do you have image of Actual repair areas versus IR predicted areas. Well, on this particular deck where we did the sounding, this was a deck where with an overlay where we were going to do epoxy injection. And so the areas that showed up there in the hand sounding outline were injected and were pretty good. Those were the areas we repaired, I guess. So that's the best correlation I have there. Um, let's see. On do you classify GPR results as DLAM or other deterioration? Well, unfortunately, we haven't been able to get the GPR results to say for sure what we're getting with because of the impacts of the chlorides on the evaluations. We just haven't been able to get good results where we can say what the results are giving us.
And there's one more question from Paul. Do you think it's worthwhile to survey driving lanes only or the whole roadway?
For us, it's worthwhile to extend out to the curbs because of the the snow and salt pile that gets accumulated in the curbs. Actually, we get I think a little bit more chloride concentration there, and so we get deterioration all the way out to the curb. So for us, it's necessary to go curb to curb rather than just in the traveled portion.
All right, we hit time 2:02. So thanks so much, Mike, for the great presentation, very informative, and also many thanks to all the participants who took the time away from their busy schedule to participate in this webinar. We had over 270 attendees in today's webinar. It's amazing. I'm glad that switching from Adobe to Teams help more people attend and participate. So the next webinar will be on May 24th, which will be focused on application of NDE on steel bridges specifically, and PennDOT will share their experience and some case studies with regards to NDE on steel structure. So I encourage all of you to attend the next month's webinar as well. So with that, I'm going to adjourn the webinar and wish all of you a great week. Please don't forget to go to the survey link and fill out the email address and answer some questions that will help future webinars. Thank you and have a great week and stay safe, everyone. Thank you.